Good morning again, chemistry students. Today we're talking just a little bit more about the modern periodic table, and in order to kind of set the stage for that, we're going to start by looking once again at Mendeleev's original table. So what you see in front of you there was one of the first tables that he came up with. This was actually a more modified version that he came up with later. The original one was actually flipped 90 degrees and had the groups going left to right rather than up and down, which is how we're used to it. But I wanted to kind of point out a few things about this one as far as how it is actually organized, right? And one of the things that we talked about that Mendeleev saw as a really important piece was the weight of the elements and used that to put them in order. And also, as we found in the periodic table activity, is that the idea of groups with similar properties, and you notice up in the top there, right? So here's our weight that he has listed there, and then notice for each of the groups he shows some of the compounds that they form, just like we did when we put together our cards with the elements, looking at those similar chemical properties. And one of the most important pieces about Mendeleev's periodic table is that he was able to use it to make predictions, just like you did in the periodic table activity. And notice that there are some blanks with dashes that have a mass next to them, even though there isn't an element symbol listed. So these are some of the elements that weren't actually discovered at the time, but he was able to make those predictions. And one of the reasons why we still keep talking about Mendeleev today was because, not just because he created this table, but because the predictions that he made were in fact correct. And if you go and look at today's periodic table, the mass of germanium is right around 72. So here's our table today. And again, key piece with this periodic table is now, rather than organizing it by mass, we have these numbers that we assign. And what you found when you did the build an atom activity, and what's important to understand here, is that we found that the patterns that arise are actually more closely tied to the atomic number. Now, atomic number and atomic mass, so the mass or the weight of the elements, are similar, but they're not exactly the same thing. So the atomic number that we use now is actually just the number of protons, whereas the weight, as you might have found, is actually due to both the protons and the neutrons. So these patterns that we use now to organize, and the number that we use to organize and put the elements in order, is based only on the atomic number, so the number of protons. And what we find is that we have a change of one proton creating a change of a new element. And as you found in the build an atom activity, each element is defined based on the number of protons that it has in the nucleus of all of its atoms. Okay? But at the same time, we still use those same groups. So here we have atomic number there, and then we also have those groups that we use. So now we give them a number, right? We also use the 1 through 18 to identify those. But we have these groups that are the same types of groups based on the same properties that Mendeleev looked at. So that part hasn't changed. The only thing that we've modified for Mendeleev's time is using the atomic number rather than the weight. However, what you should also notice here is that we are still able to make predictions about new elements. So this idea that we can use the properties of the periodic table, those patterns that are there, to make predictions of new elements. And in fact, element number 117, which I have circled there for you, was actually just discovered this summer, and they're just awaiting kind of the final confirmation to give that one its official name. And some of those other ones, those three-letter symbols, have been updated, and in fact we have all of them except for the number 117 here, which like I said is still waiting for that confirmation. Okay, so key pieces with our modern table there. Now, you also did an activity looking at the electrons, and it's important to understand why those electrons are important. And you are looking at the electron configurations, right? This first number symbolizing, so the 2 in each of these right here, symbolizing that there is 2 electrons in that first innermost shell, and then 1 more electron on the outside. And what you should notice here is that as we are going across the table, right, and again, similar, sorry, the second row, or the third row, I should say, seeing very similar trends there, but notice that now we have, instead of just 2 layers, now we have 3 layers, and I'll talk more about that in just a couple minutes. But as we go across the periodic table, okay, so going from left to right, one of the patterns that I want you to notice is that number of outermost electrons. So here we have 1, 2, 3, 4, 5. And again, I know most of you are pretty quick and probably already figured that out, but seeing that we go from 1 all the way over to 8 outer electrons. And the same thing in this row, right? Even though we now have 3, we still start at 1 and go all the way over to 8. Okay? A couple other things to point out here is that as we go down in our groups, right? So as we go down one of the groups, and again, remember these groups have similar chemical properties, they react in the same way. What we find is that we have the same number of outer electrons within that group. And again, you probably already figured that out, but I just wanted to make sure that we realize that. And as we're writing those configurations, we can see that as well. We see one outer electron there, one outer electron there, and it doesn't matter how many layers you have, all of these elements within that group all have the same number of outer electrons, right? And we can look at another group over here, group 7A, or also known as group 17, and we see that same thing happening there, right? That they have the same number of outermost electrons. And that's a really important piece that we learned later on. We didn't know this when we first designed the periodic table, but this is something that we figured out later on that just happened to support this whole idea of why the periodic table is important and why those elements have similar chemical properties, right? So that whole idea of having the same number of outer electrons is what causes it to react in that same way. And when we talk more about bonding later in second trimester, we will see why that's important. One other thing to point out here was just kind of relating also which row it's in to the number of layers of electrons. So we see in the first layer here, we have one layer of electrons. In the second row, or second period, we have 2 layers of electrons. In the third period, 3 layers of electrons. So how many layers of electrons do you think we'll see in this last layer? Well, if it's period 4, we're going to continue this same trend, and what we should see is 4 layers of electrons. One last thing to show you here is some modern variations of the periodic table, some other designs that have been created other than just a left, right, up, down, rows and columns table, is thinking more in terms of kind of a continuous streak of organized by atomic number or by atomic weight. So on the right here, the helical periodic table, where we start with the smallest element, hydrogen, and as we increase the atomic number going around, and we see them lining up very similarly into the same groups that we're used to. Similar idea here. Okay, again, hydrogen and helium, kind of those oddballs, so they kind of get their own little space here, but organized into those same groups going around a circle that we're used to. And as we get bigger, again, making those circles bigger around the outside. And here's those lanthanides and actinides that are we're used to being down at the very bottom there. So again, just some similarities to what we usually see as far as how it's lined up by groups, still organized by atomic number. Same thing here, organized into groups that are similar, still organized by atomic number, but just a slight variation on its design.